All right, hello and welcome. Today's Thursday, April 30th, and tomorrow it's gonna be May. I just did that. All right, y'all. We have this problem that we were working on yesterday for problem number 1, where G of t is the rate in tons per hour at which unprocessed gravel arrives at the processing plant. Okay, so again, like we've mentioned before, when they give you something that is written as a function, it typically is either what the function represents. So for example, I think yesterday we did A of t is the amount of something in the bin, right? So that was A of t. This is now G of t, the rate at which something is changing. So that's usually how it's going to be given, either as like, this is how much stuff is there, or this is the rate at which that stuff is changing. In this case, it's the rate at which the gravel arrives at the processing plant. So that's what G of t represents. They also tell us that they're able to process the gravel at that constant rate of 100 tons per hour, okay? So what we talked about for what is the maximum amount of unprocessed gravel, what we talked about is that is going to occur either at t equals 0, t equals 8, or when the rate that the gravel is coming in is equal to the rate that the gravel is going away or being processed and taken away. So, or when G of t equals 100, or G of t minus 100 equals 0, same thing. I said 8 and I put a 0. I meant to put an 8 right there. So when t is equal to 0, when t is equal to 8, or when the rate that it's coming in is equal to the rate that it's going out, okay? So that's what we have for this problem. And then what I would first do is figure out what this is to get, maybe other t values, whatever from there. And then we have to talk about, okay, what is the, amount of gravel, because what's the maximum amount of unprocessed gravel? So there's going to be the t, and let's say that A of t is the amount of gravel that's there. So at 0, at t equals 0, we were given that there were 500 tons. Part B asks us to find the total amount of unprocessed gravel that arrives during the workday. So that was just the integral from 0 to 8 of G of t dt, which I'll remind you what we got for that in a little bit when I look at the scoring guidelines. But that's going to go here. So we have 8 is, whatever that ends up being. And then for this, so let's go to, because I did this problem yesterday. So I'm going to go very quickly. So we found that that was 825.551. So this 825.551 minus, so that's just how much gravel was brought to the plant that day. But they also processed, they also had 500 there, and they processed 800 tons of gravel. So I should say this, right? 500 plus that minus 800. So that's what we got from part B right there. So as if I didn't need this anyway, my watch is telling me, check your rings. You're usually more active than this. Thanks a lot, watch and wife. Okay, anyway, so we have when t is equal to 8, we have the initial amount of gravel that was there, plus how much gravel was brought in throughout the day, minus how much gravel was processed throughout that day, right? And then that's going to give us, you know, this 525.551. And then we have this t value that we would find by setting g of t equal to 0, which is 4.92348. And then this amount is going to be the initial amount that was there plus the integral from 0 to 4.92348, if I didn't mess that up, 4.92348. Good. Of, so let me erase this really quickly. Of g of t minus 100 dt. So g of t, again, is the rate at which gravel is being brought in. 100 is the rate at which gravel is brought out or being processed and taken out. And so the integral from 0 to 4.92348 of that is the total net change of gravel, okay? So this is how much gravel was brought in and processed out when t is equal to 4.92348. And then you also have to add in how much gravel was already there when we started. And what we saw there is that ended up being 635.376. 635.376. And so what is the maximum amount of unprocessed gravel at the plant during the hours of operation? Well, that's going to be 635.376 tons of gravel. So it started with 500. It kept, you know, more and more was being brought throughout the day, and then they're able to process some and whatever. And when there was the most gravel there ended up being 635.376 tons of gravel, okay? Again, I just said yesterday, or sorry, 2 days ago when we did this, this is another example of the type of problem that I call leaky bathtub types of problems, right? So you have stuff coming in, the rate at which this is coming in, the rate at which it's going out, and then when the rates are exactly the same, that's when, if you take the bathtub, the leaky bathtub, that's when the water level either goes from rising to being a max and then falling, or goes from falling to being a min and then rising again. Okay, so that's what we have going on here. So that was 1D. All right, next we have 3B. Okay. Coffee maker. Speaking of that, pause. All right. Hot water dripping through coffee maker, filling up a large cup with coffee. The amount of coffee in the cup is given by this table of values. So again, the types of problems that we typically see for free response, you have either functions or derivatives of functions given, you have tables of values given, or you have graphs given, right? This is one with the table of values. So anyway, B, is there a time in between 2 and 4 at which C prime of T is equal to 2? Justify your answer. So hold on, let me first read this problem. Hot water dripping through a coffee maker, filling a large cup of coffee, or cup with coffee. The amount of coffee in the cup at any time in between 0 and 6 is given by differentiable function C. So C is differentiable. I'm gonna Excuse me. All right. So let me write that in here because that's an important thing that they tell us, that differentiable function C. Okay, so C is differentiable, where T is measured in minutes. Selected values of C of T measured in ounces are given in the table above. Okay, so it asks, is there a time in between T equals 2, so in between this and this, is there a time? Or does there have to be a time, really? When it says, is there a time, really it's, does there have to be a time in between 2 and 4, at which C prime of T is equal to 2. So C prime of T. What does C prime of T really mean anyway, right? What does C prime of T mean? Anybody?
The rate at which the coffee is going in the cup.
Yeah, right. So the rate at which, so if you are familiar with coffee makers, sometimes like in the very beginning, it might start dripping a little bit, like it'll start coming out and then it'll come out faster. And then at some point it's coming out like the fastest, and then it kind of slows down near the end, right? I've never had a coffee maker that does that and then sucks the coffee back in, meaning that C prime would never be negative. That'd be weird. But yeah, so it's the rate at which the amount of coffee in the cup is changing, which is also the rate at which the coffee is coming out of the maker, assuming we don't lose any coffee. Anyway, so just looking at, these two values, and then I'll look at these two values. Let's check this out. So in between 2 and 3, I have that from 8.8 to 11.2, that's what, 2.4 divided by 3 minus 2. So 2.4 divided by 3 minus 2. So what am I doing there? I'm taking C of 3. So let me write that down. C of 3 minus C of 2 over 3 minus 2 is equal to 2.4. What is that? What does that represent?
The average rate of change on the interval.
Yeah, so that's the average rate that coffee is filling up the cup on the interval from 2 to 3. So for this guy, we have C of 4 minus C of 3 over 4 minus 3 is going to be what? 1.6? 1.6. So if you have that C is differentiable, does there have to be a time in between 2 and 4 where the rate that coffee is filling the cup is exactly 2? What are you doing, babe?
I'm trying to find mommy because something happened to my screen. It just froze and then everyone turned off.
Okay, I'm gonna have to pause this just really quickly. Hold on. I'm gonna pause my recording. I need help, Olivia. Okay, so so does that guarantee that there must be, if the rate is coming out at 2.4 ounces per minute, that's the average rate in between 2 and 3, and then in between 3 and 4 minutes, it's coming out at an average rate of 1.6. Does it have to have been coming out at exactly 2 ounces per minute for some time in between 2 and 4? Thoughts on that? Anybody?
I'd say yes because we know it's continuous and also differentiable. So by MVT, it has to.
Okay, good, right? So by the yeah, here's the other thing, right? So okay, that's That's looking at in between 2 and 3 and in between 3 and 4. If you also just look at in between 2 and 4, right? If you look at in between 2 and 4, so between 2 and 4, we have that this average rate of change is C of 4 minus C of 2 over 4 minus 2, which ends up being 4 over 2, which is exactly equal to that 2. So the average rate of change in between t equals 2 and t equals 4 is exactly 2. So by the mean value theorem, there must be at least one C value in between 2 and 4 where C prime of t is exactly equal to 2 by exactly the mean value theorem, okay? So there are two main theorems that you need to remember for a problem like this. It's either going to be intermediate value theorem or it's going to be the mean value theorem. So those are the ones that you're always looking to use, okay? I'm going to show this now just because I think it is an appropriate time for it. So appracticeexams.com, I found has really good, notes, videos. They have found from a bunch of teachers that, teach these AP classes, not just calculus. So if you want to use this for whatever else, it's pretty good. So, but for Calc BC, if you go to like class notes on this, well, it's different people. So this is BC notes, class notes. Let's see, cheat sheet. I think this is where I saw it. No, this is just like a, overall cheat sheet that goes through a bunch of stuff. I know that I have stuff like this already on my website, but it's just some good, here's a 16-page AP Calc BC cram packet, where they have a bunch of trig formulas, differentiation formulas, integration, formulas and theorems. So if you're going down through intermediate value theorem, looking at limits as x approaches one of the infinities, all this stuff. So it has a bunch of good notes. Where was it that was on one of these guys? I want to say where it had. Yeah, he has a bunch of notes. You name it. Whatever. Area under the curve notes, and he kind of goes through and has some examples worked out and everything. So anyway, just a really good resource for you guys. But there was one, where was that? I think it was actually here, and then oops. What did I just click on? No, not this guy, but I think it was this. Anyway, definitely a lot of good resources here. There was one, and I'm not gonna, stuff you must know cold. Oh, this one I liked because it says, if you see, find the zeros, this is what you should do. If you find, take the limit as x approaches whatever, this is what you should do. It has a bunch of that all the way down, so that's another good resource for you guys. There's something that had like, these are the theorems you must know, but anyway, we'll get back to that. Anyway, so that's a mean value theorem problem. That was 3B. Looking at 5C. Okay. Oh, also 5B. So here we go. Let's look at at 5. So we want, let's bring this guy a little down. So we're given this differential equation right there. That's our differential equation. And f of x is a particular solution, and they give us an initial condition, right? So B says use Euler's method, starting at x equals 0 with 2 step sizes to approximate f of 1/2. Okay, so if I had to do an Euler's method problem with 3, 4, 5 steps, I would go through and do that method that I showed you using my calculator. For this, you're only doing 2 steps. It shouldn't be that complicated. So here's what I'm gonna say. So they give me, so at x equals 0, they give me that y is -1. Because I have two steps, what does it say? 2 steps of equal size to get to 1/2. This must be 1/4, right? So my step size is 1/4. Another way you could do that is b minus a over n. So 1/2, so this is like your a, this is your b. So b minus a over n is 2 steps, gives us 1/4 as well. This is what we call h for our step size, okay? And then the big thing, so again, I'm doing b right now. The big thing with Euler's method is to know that the next y value is equal to the previous y value plus dy dx evaluated at x sub n, y sub n, meaning the previous values, times h. So, and we know that y sub 0, or y of 0, my initial y value, is equal to -1. So, y sub 1 is equal to y sub 0 plus dy dx evaluated at x sub 0, y sub 0 times my h, right? Which, let's plug in what we know. My initial y value was -1. The derivative at x equals 0, y equals -1. So where am I? Is going to be equal to, so I plug in negative, I get 1 times 2, also known as 2, right there, okay? So that's going to be 2 times my step size, which is 1/4, which ends up being -1 plus 1/2, also known as -1/2. So y sub 1 is equal to -1/2. So if we're used to our little chart here, my chart typically had n, x sub n, y sub n, dy dx evaluated at x sub n, y sub n. This is the chart that I always had, right? So when n was equal to 0, my initial x value was 0, my initial y value was -1, and this derivative right there, I see up there was 2. When n is equal to 1, n equals 2, and then this is going to be my answer right there. So I just found y sub 1. So I know that my different x values are going to be by adding a step size, which is 1/4 each time. Those are my x values. And I just found that my new y value is, right, y sub 1 is -1/2. So then I'm going to find what is dy dx at x sub 1, y sub 1, because that's what this would be right there, right? dy dx evaluated at x sub 1, y sub 1, meaning when x equals 1/4 and y equals negative 1/2. So this is going to be, because I know my differential equation, or my this dy dx, my slope, is y squared times 2x plus 2. Y squared, 1/4 times 2 times 1/4 plus 2. Okay, so this 1/4 comes from y squared, right? Because again, we have y squared. Well, y was just negative 1/2. Negative 1/2 times negative 1/2 is positive 1/4. Times quantity, 2x plus 2, but x is 1/4. So this ends up being 1/4 times 2 times 1/4 is 1/2 plus 2. So this ends up being 1/4 times, that's going to be 5/2. So that's 5/8. So now I know that y sub 2 is equal to y sub 1, which is negative 1/2, plus the derivative evaluated at x sub 1, y sub 1, which is 5/8, times the step size, which is 1/4. So this is negative 1/2 plus 5/32. Well, negative 1/2 is also known as negative 16/32. So when I add these guys, I'm left with what? Negative 11/32. And that's my y sub 2 approximation by using Euler's method. All right. So let's check that out real quick. I don't want to show too much of C. So negative 11/32. So you can go through their calculations, but they should be similar to what we just did over here. Okay. And then I also see 5C. So now let's do C. I'm actually going to move this whole thing down. Okay, find the particular solution. If they're asking us to find the particular solution, we know that the initial differential equation must be separable, because that's the only type of differential equation that we talked about solving. Okay, we're separable differential equation. So here's what we're going to do. We start with, so there's now C. dy dx equals y squared times 2x plus 2. I'm going to separate out all my y's and dy's on one side, all my x's and dx's on the other. So I'm going to divide both sides by y squared and multiply by dx to get 1 over y squared dy equals 2x plus 2 dx. Okay? And then I am eventually going to use this initial condition to solve for my c. Right? So at this point, you integrate both sides. What's the antiderivative of y to the negative second? Well, y to the negative first over negative 1, also known as negative 1 over y. Now there is a plus c sub 1 on that side, but again, we always just put the plus c on the right side of the equation. So this is going to be equals. So here we have 2x plus 2. What's the antiderivative of 2x? Well, that's just going to be x squared. Antiderivative of 2 is 2x, and then plus c. Okay? Now, at any point after you integrate both sides, you can plug in your initial condition. So I'm going to do that now. So this says when x equals 0, y equals -1. So plugging that in, I get 1 equals c. You guys all see that? Because I plug in -1 in for y. -1 over -1 is 1. Equals 0 squared plus 2 times 0, so that's 0, plus c. So c equals 1. Okay, cool. So guess what? Well, before I plug that in, this is what we call our general solution to the differential equation. But now that we used the initial condition, so I'm going to put that general solution. And now we used our initial condition to find the particular solution. Now, -1 over y equals x squared plus 2x plus c, but c is equal to 1. Okay, cool. So now what I would do is I'd multiply both sides by -1. And I would find the reciprocal of each. So I would have y equals -1 over x squared plus 1. Okay, so something like that. You might want to say equals -1 over x plus 1 quantity squared. Let's see what they have going on. But anyway, this is going to be, either one of these is going to be my particular solution. Let's see what they have. Okay, this is a 5-pointer, right? I think I've mentioned this before, but now this year obviously is a different test, right? It's a different test because there's only 2 free response questions and whatever. But typically, when we had a separable differential equations question on the free response, on a free response question, that was usually a 5-pointer. So 5 out of the 9 points total for each problem. That was, you know, over half of the points for that problem. So 5 out of the 9. So pretty cool. Not too bad. Okay. They made a note about this being true for x greater than -1, because if x is equal to -1, that creates a 0 in the denominator. And so, anyway. Okay. Anything else from 2013, or can we do some practice problems on from what I found on those videos? You guys talk to me. You tell me what you want.
Those practice problems sound really fun. I can't wait to start them.
I was thinking the same thing. It's like, I can't wait. I can't wait. So let's do it. So let me remind you of something really quickly. And I reminded you last time as well. But so on the Google Classroom that we have, this AP Calc BC classroom that's there, I put on here the videos that review all of AP Calculus. So remember, BC is made up of AB and the BC stuff. So whatever you're looking at, you could click on one of these guys. So right now, we could do some more problems that are from, both AB and BC, or that are specifically only BC and not AB. So let's look at this. I'm just going to click on this guy. And we have, when you click on that, you have all of these videos. I want to point something out really quickly. So far they've gotten through video 27, which was, so for the past few videos, it's the different FRQ problem types. Okay, so we did tabular, graphical, algebraic, and verbal interpretations and explanations and reasonings and stuff like that, okay? And tomorrow at 6 a.m., they're gonna do AP, Calculus, BC, AP final review, putting it all together and making connections. So that's gonna be up once they have that live session. It then remains up on here, so it's not there yet because they're gonna do this tomorrow. But that's gonna be there. And then, check this out, y'all. They have some timed AP exam practice problems. That's very valuable and a good thing for you. So I definitely want you to take advantage of that. And again, it doesn't have to be live. It's cool if you can wake up at 6 and do this live, but you know, this is on Monday, I believe. Yeah, Monday at 6 a.m. And then on Tuesday, they're going to review that. And then on Wednesday, there's another timed practice. And then Thursday, they review that. And then on Friday, it's their final lesson and tips and tricks and best wishes and all that stuff. So that's up and coming. Take advantage of that, please. I put that on here because I know how valuable it is, right? This is, and you know, you guys obviously have, there are so many resources there. And if you know, I'm going to put this on my website as well, but you could just get lost and spend hours looking at the videos, at the notes, and you know, whatever about this. This practice exams, those are books that you would have to buy online and stuff. So, but anyway, so going back to where we were, right here. Let's do, there were a couple that I wanted to just kind of, you know, maybe start with. So I think I started talking about this. Did anybody do this problem yet from video 15 in the sequences of video 15? Did anybody do this yet? Okay, just Kayla did. What about number 6 from video 16? Did anybody do? So this is an Euler's method. We actually just did an Euler's method, so maybe not. How about a logistic growth? So let's. Okay, so this is again from. I'm just going to do video 17, and this is. So I don't really care about, you know, hearing them explain it. Let's just go ahead and look at this problem. I'll give you maybe a little bit of time to start it on your own. I will go through because this was a good review, so I'm going to do this. They have this on this video. So look now. All right, there we go. So let's talk about this. It says, consider the logistic differential equation dy dt equals 1/2 y times quantity 1 minus y over k. In between 4 and 20. Let y equal f of t be the particular solution to the differential equation with f of 0 equal 2. In terms of k, for which values of y is f of t increasing at a decreasing rate? What does it mean for a function to be increasing at a decreasing rate? Anybody?
Rate at
It
which
means
is slowing down. It's still increasing, but at a smaller.
So it's
Rate.
increasing, but it's kind of slowing down the rate at which it's increasing. So how can we say that using maybe derivatives?
the first derivative is positive, but the second derivative is negative.
Correct. So it's where the first derivative is positive and the second derivative is negative. So check this out. Remember with logistic growth, which, this is the form that we talked about. So they use L. I forget what he had for the carrying capacity, right? But and he has dy dt right here. I think we had dp dt for population and stuff, the rate that the population is changing. But anyway, dy dt equals k times y times quantity 1 minus y over L. L is what we call that carrying capacity, or the limiting size is another way of saying that. And so the limit as t approaches infinity of y is just that L. So what we said graphically, what's happening here, graphically what we have is, this is what it's going to look like. Oh man, I don't want that guy. So this guy starts looking exponential. And then at some point there, some guy there, which is some height here, it's then going to go like that. And check this out. Oh no, I just wanted to like stretch you. There you go. So this guy right here, this is going to be the carrying capacity. So in this, for this problem, this is L, right? Because they have L there as our carrying capacity. Well, this right here is going to be L over 2. That point, so when the y value is half of the carrying capacity, that's when the function, whatever that function is, whether it's a population of animals or whatever it is, that's when that thing is growing at the fastest rate. So increasing at the fastest rate. And then it starts increasing still, but at a slower rate, okay? So that's what we got going on right there. So now let's go back down. So this would be the t value that you would have to plug in to find, if you're given the carrying capacity, whatever that limiting size or carrying capacity divided by 2 is, that's the time that is associated with that. So let's go back down now that we've kind of reviewed that a little bit. Let's go back down to this. What is K that they're talking about? I don't know. What is K? Just looking at this logistic differential equation, what is K for this? What is K referring to?
K is the carrying capacity.
Yeah, K is what they have right down there in the denominator of this, y over something, which just like what we had up there, here they had K as this, relative growth rate. But here they have k down there, right? So don't let it confuse you that they happen to choose k. I think it's silly that they chose k because they just gave this formula. But k is located down there, and k is just a variable, or a constant, I should say. So that right there is going to be the carrying capacity. So in terms of k, for which values of y is f of t increasing at a decreasing rate?
From k over 2 to k, but an open interval, because it never actually equals those, or because at k over 2, it's an inflection point, not actually concave down.
Right, it's one of the endpoints, so you wouldn't include it. So yeah, right, from k over 2 all the way through k. So for which values of y, again, going back up here, it's asking for basically these values, the y values, where, because you see the projection of this, the y values for all of those guys, we have a function that is increasing at a decreasing rate. So it's going to be from whatever the carrying capacity over 2 is up to the carrying capacity. So this would be from L over 2 to L, but down here it would be from K over 2 to K. All right. I haven't watched this video all the way to see their explanation of it, but let's go through a little bit. Oh, this is good. I did watch this. They go through like these quick check 1 and 2 and just going through different different like problems to make sure that you you get that. So that's those are good things to look at. Okay, so here they go through. This is so he just answered that right there. I just ended up going to, oh, I guess. Okay, so that's their explanation of it. So anyway, if you see, these videos are pretty good, and I like, so this is just part A. We're gonna go on to part B right now and maybe talk about, he goes on if you want to continue watching this, we are at like 23 minutes, 45 seconds into this video. He goes through a little technology thing, whatever, but let's go to part B. Find the second derivative of y with respect to t in terms of y and k. So I want to give you guys like 2 minutes. I want you to try to do this problem right now. So they give you this problem, and they ask you, or this differential equation that is a logistic differential equation, and they want you to find the second derivative of y with respect to t. So I'm going to give you 2 minutes. I'm going to pause this recording for like 2 minutes right now, and I'm going to give you 2 minutes to do that, and then that might do it for us. But go ahead and do this for 2 minutes. Go ahead. All right, are you guys still working, able to do it? I'm going to go ahead and show you what I did. So obviously this is the first derivative of y with respect to t. And so what I did is I actually simplified that a little bit by distributing through by the 1/2 y to get 1/2 y minus 1/2k times y squared, like that. I then differentiated both sides with respect to t. To get that, the second derivative of y with respect to t is equal to, okay, so here we go. What's the derivative of 1/2 y with respect to t? Well, remember that's implicit differentiation. You have to take the derivative like you normally would. So the derivative of 1/2 y would be 1/2 times dy dt minus. Now here, the derivative of 1/2k times y squared, again, k is a constant, right? It's just that carrying capacity. So when you take the derivative, that the power rule, that 2 is going to come down and cancel out with the 2 in the denominator. We're going to have minus 1/k times y times dy dt. So this ends up being, if you factor out, let's say, I'll call this 1/2 minus y/k times dy dt. Now, you shouldn't leave it like this because they say find this in terms of k and y, not in terms of k, y, and dy dt. So what is dy dt? Go back up there and say, oh, dy dt is just that. So I'm going to replace the dy dt with 1/2 y times quantity 1 minus y/k. So that's what I have. Let me rewrite it. The second derivative of y with respect to t is 1/2 minus y/k times this 1/2 y times quantity 1 minus y/k. That's what I would have. Or that's what I got. Now, I'm curious because so first of all, does that make sense for you guys? Any questions with what I did there? You see how you have to use implicit differentiation? Someone just knocked on our door. Okay. No one's answering. So I think that made sense for you. So when I look at the video, I don't understand what he means here, and I don't, when he says, I don't know what he means by that when the solutions are released later on. Does anyone know what he's talking about? I don't know. Anyway, that kind of brings us to the end of our time for today. Oh, you can't hear him? Oh, man. That's my bad.
Implicit differentiation would be even better. But the problems like this have shown up in the past
Can you
in the
hear
AP
now?
exam. It takes me back to the baby bird problem. Teachers, you may know what I'm talking about. Students, you may have solved that in your class. But it's a very poignant way to have the students exercise their ability to know implicit differentiation. And there's all sorts of questions that can be asked based on the result of that second derivative. So definitely try that problem, and you can check it in the solutions when they are released later on. But I do want to go ahead and turn.
Anyway, that's part that I didn't understand what he meant. Anyway, what I want to point out for that problem that we just did, obviously logistic growth is a BC only concept, yet the part B that we just did is an AB concept. Finding the second, that was just implicit differentiation. So that's what we got going on there. Anyway, that's what we got going on for today. I do want to, I'm torn because there are a lot of different things I want to just allow you to do. And typically I assign, okay, now look at the 2012 and that's what I have, but here's what I'm gonna say. I really want you to look at the videos instead of just focusing on more problems, which you guys totally can. You know what types of problems I've been assigning. They're typically the ones that are either AB or the BC that don't have the, you know, parametric, polar, or a bunch of the series stuff, because that's not going to be on the test. So focus on the other questions. So if you want to focus on that, you can. I'm not going to assign you have to do these problems from this year's test for the weekend, but I do want you to look at these problems from you know, what I posted for the AP you know, calculus curriculum, or whatever, this appracticeexams.com, and I'm going to put this as on my website, as a link on my website, and also in the in fact, I'll do it right now with you guys here. I'll say so there you go. You have it on in Google Classroom. Maybe I'll just leave it there. But you know, check that out. Like I said, there are a lot of really good resources there. They do, for example, for videos, they reference Khan Academy. There's also this teacher who has 83 videos that just go over a whole bunch of concepts. So the resources are just, you know, there are so many. And I don't want to bombard you by saying you have to look at these, but just know there's so many resources out there. If you're struggling on any particular concept, you know, Euler's method, or, you know, whatever it is, my approach would be, first and foremost, on this, you know, right here site, I would go through, if it's, you know, an AB or BC concept, and say, oh yeah, I really want Euler's method, you know, and then, you know, you go through.
In front of the x squared, we have this arbitrary k. So now, in prep for the 2020 year, we're so glad that you're joining us today.
Right?
Today,
they go over and they review everything, and then they give you.
Doing fantastic. The sun is.
There's a little bit of small talk in between.
Too many of these animals in Austria.
They do a solid job.
These ideas together, and we create this more evolved free.
Anyway, that's where I would start. After that, I would probably hit up, you know, just, you could do a simple search, or you could go to, you know, notes or whatever it is on here, or definitely Khan Academy. You know, my website also has a bunch of stuff that, you know, there is this full review that I posted before where you did the practice exams. There's also, there's so many resources out there. So I don't want to bombard you with them, but if you're having a tough time finding those resources, please let me know, and I can, you know, be more specific in my direction. But I just feel like I want you to take this on your own. I also feel like usually I always emphasize getting in study groups and doing whatever. You guys can do that, whether that's via Google Meet, so virtually, FaceTime, or whatever, however you want to do it, right? You guys can meet that way virtually and help each other out. I think that's you guys are valuable resources to each other. So that's all I got for you for today. We'll resume on, well, tomorrow I will be here starting at 9 to reteach, answer any questions, whatever you want, but I am going to open that up to my engineering students as well. So at 9, I'm just going to be here for answering questions and doing whatever you guys want to see. Okay? All right, y'all. Anything else? All right, guys. Have a good day. I'll see you guys tomorrow, or otherwise I'll see you Tuesday, and have a good weekend.
Bye, girl. Have a good one.
All right.
Have a nice day.
Later.